Hello and welcome to Controllers Tech. This is the 10th video in the STM32 ADC series, and today we will look into the reference voltage. This is going to be a very confusing video, so pay attention to every detail. I will explain why this reference voltage is an important parameter in the ADC, and how to measure this voltage using the internal reference voltage of STM32. We will also see the availability of the reference voltage pin on different STM32 dev boards, and even if the pin is available, how to actually make it useful in our application. I will demonstrate the measurements on 3 different dev boards, the Nucleo F446, Blue Pill F103, and the H750 based custom board. Let's quickly take a look at the different types of voltages we are going to see in the video. At first we have the VDD and VSS. These are the main supply voltages. The VDDA is the separate analog supply, and it is used to power the analog circuits in the MCU. In almost all the STM32 devices, the VDDA is connected to the VDD. Next we have the VREF, the reference voltage. This is basically the voltage with which the ADC input voltage is compared, and then the digital value is calculated based on the comparison. For example, if the VREF is at 3 volts, an input voltage of 1.5 volts will result in the digital value of half the max value. In the low-pin package MCU, a separate VREF pin is not available, and it is connected to the VDDA itself. Whereas in some high-end MCUs, the VREF pin is a separate pin, and we can use it to provide custom reference voltage for our ADC. There is another reference voltage, VREFINT. This is the fixed internal reference voltage, which can be used to measure external reference voltage. The VREFINT has a fixed value, and it does not vary if even the main supply voltage is reduced. Before we proceed with the video, just make sure you have the reference manual, datasheet, and the schematic of your board. I will start with the Nucleo F446 first. Let's open all the required documents for this dev board. We will start with the reference manual first. Go to the ADC section, and here you will find a table named ADC pins. As I mentioned earlier, the VREF is the external reference voltage, used for comparing the ADC input voltage. The ADC input voltage cannot be outside the VREF limits, or else the data will be limited to these voltages itself. The VDDA and VSSA are the separate analog supply voltages as discussed earlier. Now we know that the VREF Plus is a separate reference voltage for the ADC, but it has some limits, and you can find these limits in the datasheet or reference manual of your controller. Here for F446RE, the VREF Plus can be between 1.8 volts to VDDA. Whereas the VREF Minus is connected to the VSSA, which is then connected to the ground of the MCU. Even the reference manual says that VREF Plus and Minus pins are available in the MCU, that does not mean that your board will have it. Let's open the datasheet to investigate it more. Here search for the VREF Plus, and let's keep going until we find something useful. Here you can see for the 64 pins package, the VDDA and VREF Plus are assigned the same pin. So basically these signals are interconnected, and hence we cannot provide a separate voltage to VREF Plus. Similarly, VREF Minus and VSSA are interconnected, and we already know that VSSA is connected to ground, hence the VREF Minus is grounded too. On a 100-pin package, we do have a separate VREF Plus pin, but the VREF Minus is still connected to VSSA. Having a separate pin simply does not mean that we can provide separate voltage to VREF Plus, but now we need to check the schematic to figure out how this pin is connected. By default in every board I have seen so far, the VREF Plus is always connected to the VCC, but after making some hardware changes, we can separate this pin. We will see this in the H750 dev board. Let's keep looking for the VREF Plus in the datasheet. Here you can see the ADC characteristics. This table lists all the conditions required for the ADC. The VREF Plus voltage can vary from 1.7 volts to VDDA, whereas the VDDA can vary from 1.7 volts to 3.6 volts. Now let's look for VREFINT. As discussed earlier, VREFINT has a fixed value, therefore this can be used to measure the external reference voltage, or the main supply voltage itself. For the F446RE, this internal reference voltage is around 1.21 volts. The calibration value for this voltage is stored in the memory of the MCU during the manufacturing process. As mentioned here, the calibration was done for the VDDA at 3.3 volts, and the values are stored at these addresses. I am using Nucleo F446, which is a 64-pin package, hence the VREF pins are tied to analog supplies. Also, as you can see in the schematic here, the VDDA is connected to the VDD, the main supply voltage. So in the case of Nucleo F446, the reference voltage is always the same as the supply voltage. Therefore we will use the internal reference voltage to measure the supply voltage of the Nucleo board itself. Imagine a scenario where you want to use the ADC on this board, but the board is battery powered. As the time passes by, the battery voltage will drop, and so will the supply voltage. If the ADC is configured to always refer to the 3.3 volts, the ADC readings will be wrong when supply voltage drops below 3.3. Therefore it is always recommended to measure the current VDD, so the ADC reference point can be updated accordingly. As the datasheet shows here, the minimum sampling time required for the VREFINT is 10 microseconds. I have already created a project for Nucleo F446. Let's see the configuration used in this project. The system is running at maximum 180 MHz, whereas both the APB clocks are at 45 MHz. This means that the ADC clock is also at 45 MHz. I have enabled the VREFINT channel of the ADC1. I am using a prescaler of 8 to reduce the ADC clock, and the sampling time is set to 480 cycles. With the current setup, the ADC will take around 87 microseconds to convert the internal reference channel, which is more than 10 microseconds, so it is fine. Let's enable one more ADC channel, where we will supply the input voltage. Now we are doing two conversions, so enable the scan conversion mode, set the number of channels to 2, and configure the channel 0. I am going to use the DMA for multiple channel conversion. Make sure the DMA is in circular mode for the continuous conversion. Also enable the DMA continuous request. Alright, everything is configured. Click Save to generate the project now. The VREF calc retrieves the calibrated data from the memory. This is mentioned in the datasheet of the device. Also note that this data was measured with VDDA at 3.3 volts, which is also mentioned here. Now inside the main function, we will start the ADC in DMA mode to read 2 channels. Once the conversion is finished, an interrupt will trigger and the conversion complete callback will be called. Inside this callback we will calculate the actual reference voltage using the converted value. This formula is defined in the reference manual of H750. After calculating the reference voltage, we will use it as the reference point to calculate the ADC input voltage. Alright, the project builds just fine, so we will load it to the board. But before doing that, let's make some hardware changes, so that we can vary the VDD. This jumper on the Nucleo board enabled it to receive the power supply from the ST link. When this jumper is connected, the VDD will be set to 3.3 volts. I will leave the ST link connected, but remove this jumper. Now I am supplying the power on the 5 volt pin of the board. Right now the supply voltage is set to 1.7 volts. Let's try to launch the debugger. Well, it did not work, as we know that the VDD needs to be higher than 1.8 volts. Now I am changing the supply voltage to 2 volts. The debugger has launched successfully. Let's run it now. You can see the VREF is being shown 2000 millivolts. Now I am going to vary the ADC input voltage. Also keep an eye on the ADC value. Now the input voltage is 1 volt. The ADC value is around half the maximum, and the voltage variable is showing 1000 millivolts. Now the input voltage is 2 volts, same as VDD. You can see the ADC value is at maximum 4095, and the voltage is also around 2000 millivolts. Now imagine if the battery voltage drops to 2 volts, and we do not measure the reference voltage. Our reference point is set at 3.3 volts. The ADC will still measure 2 volts as 4095, and our calculation will show this as 3.3 volts input voltage. Now I am increasing the supply voltage to 2.5 volts. The reference voltage is also changed, and the ADC will now measure the input voltage against this 2.5 volt reference. Therefore the ADC value has been reduced. But because we are setting the VREF as our reference point, our calculated voltage is the same as input voltage. Now we can measure the input voltage up to 2.5 volts. This is how the VDD affects the ADC, and therefore when using the battery to power the system, you must set up the ADC to measure the VDD. Note that the method we used is to measure the VREF, but since in Nucleo F446, the VREF is connected to VDD, we are getting the measurements for VDD itself. Now we will do the same in F103 Blue Pill. Let's open the manual and datasheet of this MCU. Let's start with the datasheet and search for the VREF+. Here you can see the VRE+ pin is available in a 100 pins package, but it is not available in 64 pins. It must be connected to the VDD-A. It is also not available in a 48 pins package, and must be connected to the VDD-A. If you do have a separate VREF+ pin available on the board, it must have a voltage between 2.4 volts and VDD-A. The VDD also varies between 2.4 volts to 3.6 volts. Let's look for the VREFINT. Here you can see this voltage is fixed at around 1.2 volts, but unlike F446, this MCU does not have a calibration data for the VREFINT. Don't worry about it, as we will get the data ourselves. Here I have already created a project for F103C8. Let's check the Cube MX configuration once. Also note that the sampling time for the internal reference channel must be between 5 to 17 microseconds. Here I have enabled the VREFINT channel in the ADC1. The channel sampling time and ADC clock is set so that we get the conversion time between the specified limits. In the main code we will simply read the ADC value for the internal reference channel. The board is powered with 3.3 volts right now, and we got the ADC value 1530. Make sure to call the calibration function once before starting the ADC. Now we will use this 1530 as a calibrated value for the internal reference voltage. Finally calculate the VREF using the calibrated value we just defined. The calibrated value we calculated was using 3.3 volts VDD, hence the 3300. To provide the variable power supply, we need to remove the 3.3 volt supply from the SD link, and then connect the external power supply to the 5 volts pin of the board. Right now the supply voltage is set to 2.5 volts. Let's debug this project. You can see the VREF is around 2400 millivolts. Now I am increasing the supply to around 2.8 volts. You can see the changes in the debugger as well. When the battery voltage drops, the VDD will also drop, and so does the VREF. As long as the VREF is above 2 volts, things will work just fine. We can use this measured VREF to calculate the ADC input voltage. So we saw the two MCUs so far. In both of them, the VREF pin was connected to the VDDA, which was then connected to the VDD. Hence we could not have a separate reference and supply voltages. If you take a look at the schematic of the H745 discovery board, here you can see the VREF plus pin is separate from the VDDA. But there is a 0 ohm resistor connecting both of them, which is then connected to the VDD of the MCU. So by default the VREF of the board is connected to the VDD. If we remove this R66, the VREF pin will be completely independent, and we can provide a separate reference voltage for the ADC, while the MCU is still running at VDD. But removing R66 alone will not be enough on this board. Here you can see the physical VREF pin is not connected to the MCU's VREF pin. So we need to also close this SB20 connection to connect them both. Once both the changes are made, we can provide the external reference voltage for the ADC. Now I did not do it on this board as this is very expensive. But I did something similar on the H750 custom dev board. Here you can see the schematic of this board. The VREF pin is connected to the 3.3 volts, via this 0 ohm resistor R11. I removed this resistor, and therefore the VREF becomes open. We can then connect the external reference voltage on this pin. Also note that VDDA is a separate pin, which is connected to 3.3 volts, via the R34. Let's take a look at the datasheet of this H750 MCU. We will again look for VREF+. Here you can see the range for VREF+ is between 2 volts to VDDA. We should keep this in mind when providing external reference voltage for the ADC. If you want a lower reference, disconnect the VDDA from 3.3 volts, and provide external voltage for the VDDA as well. Now we will look for the VREFINT. Here we have a typical 1.216 volts for the internal reference voltage. And there is calibration data for the VREF, stored in the memory as well. Alright, I have already created a base project for H750. Let's configure the ADC 1 channel 3 in single-ended mode. This is where we will measure the ADC input voltage. Let me first fix the ADC clock issue here. The ADC is clocked at 75 MHz right now. Let's use a high prescaler so that the measurement will be slow. I am also enabling the DMA in the circular mode, so the conversion and transfer will take place using the DMA. Let's set a high sampling time for this channel, so that we do not interrupt very often. The internal reference channel is in ADC 3, so we will enable it there. Let's configure this channel so that we get the sampling time higher than 4 microseconds, as specified in the datasheet. We will read this channel in the blocking mode, so no interrupt or DMA is needed. Alright, that is all. Click Save to generate the project. Let's define an array to store two ADC values. We will store the calculated VREF here, and the input voltage here. Now let's fetch the calibrated VREF data from the memory. Now inside the while loop, we will convert the VREFINT channel of the ADC3. I am storing the value in the first element of the array. Inside the main function, start the ADC1 in the DMA mode. We will read the input voltage here, and the ADC value will be stored in the 0th element of the array. Once the DMA finishes the conversion, we will simply set this variable to 1. Now inside the while loop, first calculate the VREF voltage using the calibrated data, and the ADC value of the internal channel. If the variable, is set to 1, we will use this VREF as the reference point to calculate the actual input voltage. That is all. Let's build and debug this project. This is the connection for this board. The board is powered with 3.3 volts from the SD link itself. Therefore the VDD is fixed at 3.3 volts. Although I am providing a separate power supply to the VREF plus pin. Let me adjust it to 2 volts. The Active Pro will be used to provide a variable input voltage to the ADC input. Let's run the debugger now. You can see the VREF is at 200 mV. Keep in mind that VREF is a separate pin here, hence the VDD is not being changed. It is still at 3.3 volts. Now I will vary the input voltage to the ADC. You can see the voltage value is updating according to the input voltage. Also keep an eye on the ADC value at the 0th element. This is the value as per the input voltage. You can see that at 2 volts, we have reached the full resolution. This is the advantage of using an external reference voltage. Say for example, if the sensor outputs the voltage between 0 to 2 volts. We can use the external reference voltage of 2 volts to get the full-scale resolution of 16 bits. You can see at 0 volts, we are getting the value around 1000, whereas at 2 volts, the value is around maximum 65,535. If you do not want to provide an external supply on the VREF pin, there is one more way to generate a fixed reference voltage. Some of the STM32 devices are provided with the VREF buff peripheral. It is used to set a predefined reference voltage on the VREF pin. We can enable the internal voltage reference here. You can see the pin VRE+ is now configured as VREF buff out pin. You can even connect it to the sensor's VCC to power the sensor. But it is capable of providing a very small current, somewhat around 4 mA. We have only a few sets of voltages available here, so I am going to set it at 1.5 volts. Alright, let's generate the project again. Although we do not need to measure the VREF now, but I will keep the code same, so that we can see if the VREF voltage is generated as per the configuration. Let's debug the project. I have removed the external supply on the VREF pin and the 1500 mV you are seeing is generated internally. Let's vary the input voltage. You can see that the ADC value has reached maximum at 1.5 volts now. So we are getting a full-scale resolution at 1.5 volts. But still the VREF is not exactly 1500 mV. Let's do the calibration for ADC3 once. Let's call the calibration function inside the main function. The calibration mode is set to linear calibration offset, and the channel is configured in single-ended mode. Alright, let's build, and debug it again. Now you can see we are getting the reference voltage of 1500 mV. Actually the calibration is required for measurement, not the generation. So even if it is not calibrated, the voltage generated is still 1.5 volts. The error was simply there in the measurement of the VREF. Like I said earlier, since we are generating it internally, we do not need to measure it. So you saw how we can use the external reference voltage to reduce the reference point for the ADC input voltage. This can help us get the maximum resolution, even at the low voltages. Also for the devices, where a separate VREF pin is not available, we can reduce the VDD itself. So I hope you understood the reference voltages used in the ADC peripheral of STM32. This is it for the video. You can download the project from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.